In this video, I'm going to do a general overview of parametric surfaces. In much the same way that we describe a space curve by vector function r of t of a single parameter t, we can describe a surface by vector function r of u of v of two parameters u and v. So just going back to that space curve, r of t with our parameter t. Now we're talking about a two-variable vector function, r of u of v, and that's going to give us a surface in 3 dimensions. So we suppose that r of u of v equals x as a function of u and v, y is a function of u and v, j, and your z, a function of u and v, k, is a vector valued function defined on a region D in the uv plane. Alright, so x, y, and z, the component functions of R, are functions of two variables u and v with domain D. The set of all points x, y, z, and R such that x equals a function of uv, y is a function of uv, and z is a function of uv, and uv varies throughout D is called a parametric surface S, and equations 2 are called parametric equations of S. So hopefully we have a picture here. Yep. So we have our domain D and our surface S, right? So each choice of UV gives a point, right? It gives a point on S. By making all the choices, we get all of S. So in other words, the surface S is traced out by the tip of the position vector R of UV as UV moves throughout the region D. So you can imagine R of U moving and just like tracing out that surface for all of U, V, and D. So, well, quickly, we're just going to go through example 1. Identify and sketch the surface with the vector equation. So you're looking at this is your x, this is your y, and this is your z. We have the parametric equations as noted. And you'll see that if you take x squared plus z squared, you end up with 4 cosine squared u plus 4 sine squared u. All right? And then Pythagorean theorem, we get 4, right? So this means that the vertical cross sections parallel to the xz plane, right? That is with y constant, are all circles with radius 2, right? So you'll see that since y equals v, right? There's no restrictions on v. Right, so the surface is a circular cylinder with radius 2, whose axis is the y-axis. If a parametric surface S is given by a vector function r of uv, then there are two useful families of curves that lie on S. So this is just the second step. So we're talking about r of u and v, but we also want to talk about the two useful families of curves that lie on S. One family with u being constant and the other with v being constant. So these families correspond to vertical and horizontal lines in the uv plane. Alright, so if we keep u constant, right, so we put u as u of 0, u naught here, then r of u naught v becomes a vector function of the single parameter v and defines a curve C1, right, that lies on S. So you can get this curve C1 by keeping the u constant. And so goes for C2, right? So C2, your v is constant. So we talk about that here. Similarly, if we keep v constant by putting v equals some constant v naught, we get a curve C2 given by r of u of v naught that lies on S. And we call these curves grid curves. So example 1, for instance, the grid curves obtained by letting u be constant are horizontal line, whereas the grid curves for v constant are circles. So in fact, when so then the book starts talking about in computer graphics, graphs of parametric curves, it usually depicts the surface by plotting the grid curves, right? As we see in this next example. Okay, so we've got this curl here. So yeah. So we can define these grid curves by having v is constant and u is constant. So you see that in the sphere, this tube, right? Spiral tube. All right. So I'm not going to go over example 2 or 4. Sorry. That we'll talk about parametric representations in the next couple videos. But I just wanted to get the point across. What a parametric curve is, surface, how to define that, and then talk about the grid curves that we had just talked about. Right here, you can see the grid curves. All right. Thanks for watching.